You have a microphone?
It's for a wide microphone.
Oh, okay. So if I stand there,
without the mask, and then you can speak easy.
over here?
Yeah.
Okay, that's where it is physically. So I'll take off the mask. So take your distance now. Okay. Right. Dames en heren, geachte collega's. Ik heet u van harte welkom op de openbare doctoraatsverdediging van Fabio Malizia en verklaar de zitting voor geopend. De heer Fabio Malizia, laurea magistrale in aerospace engineering at the University of Bologna, heeft aan de faculteit een proefschrift voorgelegd handelend over modeling of wheel aerodynamics and its impact on cycling. In het Nederlands modelleren van wielaerodynamica en de impact op het wielrennen. Dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. Hij zal dit proefschrift nu verdedigen. Ik vraag aan de kandidaat eerst een uiteenzetting van ongeveer 45 minuten te geven over zijn werk. Daarna zal er gelegenheid zijn tot het maken van opmerkingen en het stellen van vragen. Zo, Fabio, je...
Welcome, everyone. I want to start this presentation with a question. How do cyclists win a competition? Actually, there is not a simple answer for that, but one approach that is very common in the last days, in the recent years, is marginal gains. We try to break down everything that goes into riding a bicycle in every tiny aspect and try to improve it. Even the smallest improvement on the smallest aspect, when you sum up all them together, you will get a competitive advantage against the...
Are you sure that the jury members remote can hear you and see this slide?
I think so. Are they online, the jury members? They are all online.
Just checking.
No problem. Okay. And if we put all together, they can give a competitive advantage against the opponents. And what does it mean in cycling? It means improving training, nutrition, but even the smallest aspect, like the pillow where you sleep, but also improving equipment and choosing the right equipment. But what does it mean arriving first? Sometimes it's really a matter of small margins. And I want to give you 3 examples. The first one is Tour de France 1989, more than 3,000 kilometers, almost 88 hours of cycling, and the time difference between the first, Le Mans, and the second, Fignon, was only 8 seconds. Le Mans gained the 58 seconds in the last stage, an individual time trial. And as you can see from the 2 pictures, the equipment they choose was very different. Fignon had 2 disc wheels, but it didn't have any helmet, and his ponytail was flapping in the air. While Le Mans had his aero helmet, aero water bottle, 1 disc wheel, and also the aero bars. And Kyle in 1989 found that even just cutting the ponytail would have given Fignon 8 seconds, exactly what he needed to win the Tour de France. The second example, it's the sprint in the Olympic Games. It's a 200-meter race with the flying start. Actually, you have to win 2 out of 3 of these races. And Christina Vogel won against Rebecca James only by 16,000 of a second and 4,000 of a second. As you can see from the picture, the difference between the 2 in space is very small. The equipment this time is rather similar, but they for sure drive 2 different bicycles. Their helmets are slightly different. For example, Vogel had a shorter helmet, but again, there is a difference in the wheel they're using. Vogel used a 5-spoke wheel, while James a 3-spoke wheel. The third example is the Tirreno Adriatico 1,000 kilometer race, 20 5 hours of racing, and Roglic last year won by only 0.31 seconds. And he gained 26 seconds in the last stage, a time trial, which is actually held in my hometown in Italy, San Benedetto del Tronto. And if we see the pictures, again, there is a different equipment that was chosen. Yates used the aero helmet, but not a visor, sunglasses, while Roglic used the aero helmet with a visor in front of him. Roglic didn't have a water bottle, he had a 3-spoke wheel, while Yates had an aero water bottle, but a spoked wheel, a wheel with many spokes. 30 times we have a different wheel in front of the bicycles. Then we have shown that a small margin can make really a big difference in a cycling competition. It's both single races and multi-stage races. Now I will introduce something we will see later. Aerodynamics is actually the major resist force, up to 90% on a flat stage when you are riding fast. And through the mathematical models, Martin et al. Showed that even with a 2% drag reduction, it could achieve, cyclists can achieve a significant reduction in time. As we can see, these differences were always significant for the previous example. Then, small conclusion of this introduction, even a small aerodynamic drag reduction is effective to improve the performance of elite cyclists. Now, the contents of the presentation, after the quick introduction, we will go to the state of the art and research gap, then the objectives. Then I will do a step back. I will show the physics of cycling and the methodology I applied. And then we go to the results of my research project and then conclusion. Now, cycling aerodynamics includes many aspects. As we see here, Roglic driving a bicycle. We have the cyclist. Different cyclists have different anthropometric characteristics. They can have different position on the bicycle. They can wear different skin suit, different helmets, and also the helmets can have different designs. Also the handlebar, which influence the cyclist's position. The frame, of course, every manufacturer has its own frame. But again, also the wheel. The wheel can have different types, disc wheel and the spoked wheel in this example. But also the spoked wheel can have many spokes, different shape of spokes, rim depth. They can have, there are many different designs. And cyclists don't ride alone usually. And then there is also to take in account the drafting. As we see, it's very complex. Aerodynamics, cycling aerodynamics include many aspects. And therefore, there are reviews which try to synthesize and give conclusions about cycling aerodynamics. Now, there were already reviews about cycling aerodynamics, but they mainly focus on the most modern state of the art, and they focus mainly on the published material, only research done by researchers in academia. While there were also past innovation, which had a role in the past. Even 100 years ago, we found some aerodynamic innovation in cycling, the first pictures from the left, for example. And we need also to take in account the innovation in aerodynamics made by manufacturers, because actually they also make the state of the art. If we narrow our focus on the wheel, we see that in the Tour de France is riding right now, there are 4 different wheel manufacturers for the 22 teams. Every manufacturer produces different type of wheels, spoked wheels, 3-spoke wheel, disc wheel, and even different types of these wheels. For example, they have different spoked wheels with different rim depth according to every situation of the race. But the previous research that was done in cycling aerodynamics mainly focused on comparison of these wheels, since there were so many designs. But there are discrepancies between the different studies, and we found also a lack of uniform testing, and this is also causing the discrepancies. And about these two aspects, I will show some slides now. Greenwell and Tew and Sawyers tested two wheels that were the same, a spoked wheel and a 3-spoke wheel. And at 0-degree U angle, meaning that when the wheel is aligned with the floor, they found even a 37% drag difference. As we remember at the beginning, we talked about marginal gains. 37% of difference is quite high when we have needed to choose also the right wheel. The second example is God et al. He reported his CFD simulations, their CFD simulation, and some wind tunnel tests performed available in the literature. Changing the U angle, meaning when there is a crosswind, the difference in the wind tunnel results vary between 10 and 40%. The trend is not really the same, and even the CFD simulation don't have the same trend of this wind tunnel test. Higher discrepancies even found at the 0 degree U angle, the red column on the left, where we found some tests that provided a drag coefficient of 0.02, while other 0.05. This difference is really quite substantial when you have to choose a wheel. If we go to the CFD simulation, the situation is not much better. There are 6 previous studies that investigated wheel aerodynamics, and the settings they used vary significantly. For example, talking about the computational domain, as we see already from the picture, in some cases we have a computational domain very close by the wheel, in other cases much larger. The grid sometimes is smaller than 1 million cells, other times 60 million cells. And also the way the wheel rotation was modeled, there are 3 different approaches were used, and about the turbulence modeling, 4. This means that there is a lack of confidence in the actual simulation methodology, and meaning also, for me, when I started this research project, I actually didn't know which settings I should have used. Therefore, I identified this research gap. We need an extensive literature study, also to not talk only about the recent state of the art, but also the past one, and include also the innovation made by manufacturers that had a contribution to actual records or competition, to win a competition. When we talk about wheel aerodynamics, we need to know the impact of computational parameters and physical parameters, and also to understand the difference between testing or simulating a wheel isolated or together with the bicycle and the cyclist, because often the wheel is simulated or tested alone. Therefore, the objective of my thesis, the main one, is perform an aerodynamic investigation in cycling with main focus on spoked wheels. This means this yields to 3 sub-objectives: describe the development and state-of-the-art of cycling aerodynamics, then establish a fair framework to perform CFD simulation of spoked wheels, and then lastly, evaluate the differences between isolated and non-isolated wheels and static and rotating wheels. Then, now let's do a step back, showing the physics of cycling. Let's consider a cyclist riding uphill. It will be subjected to different forces. For example, the bearing in the wheels will cause a power loss. Then there will be the wheels will touch the ground and will be subjected to a rolling resistance. Then the cyclist and the bicycle has a weight, and this weight, when you go uphill or downhill, will have a component parallel to the ground, which will slow down when you go uphill or accelerate the cyclist when you go downhill. Then lastly, there is the aerodynamic force, which is the one in red, FD, but often is neglected. Also, there is an aerodynamic moment caused by the rotation of the wheels. Often this quantity is not taken into account in the model simulation. If we put all together, including also the efficiency of the chain transmission, it is this eta C, we can have our model. But what I want to show here mainly is the dependence of every quantity to every force and moment to the velocity. The aerodynamic terms are dependent by the square root of the velocity, while the rolling resistance doesn't depend on the velocity in this model from Martin et al. There are some papers recently that question this dependence, but in general, we will consider here that they are not dependent. Then the potential power loss due to the weight is not influenced by the velocity, while the bearing friction has a velocity term in the equation. Then, if we play with this model and we put as input like a cyclist of 70 kilo, a bicycle of 10 kilo, an average drag area of 0.3 meters squared, and when you're riding on a flat terrain at 0%, you can see that aerodynamic is the major resistive force when we are at high speed, almost 90%. Then, if we vary the drag area, which is a quantity related to the aerodynamics of the cyclist, from 0.2 to 0.4, there will be a difference of almost 10 kilometers per hour. Even when we go uphill, there will be a grade from 0 to 5%. Aerodynamics stays at the beginning when the grade is not, the uphill is not high, much high, the slope. The aerodynamic power loss is still the major resistive force. while going more uphill, the potential power loss will be the major resistive force, but still aerodynamics play an important role. However, at the end, this was mathematics, but how fast can you go with a bicycle? These are 3 examples. Per V, in the world record of 200-meter race, he managed to achieve an average speed of 77 km/h. If now we question what is a bicycle, and we not consider the bicycle the usual we ride, but we consider a bicycle also a vehicle with 2 wheels, just with powered by human, and with an aerodynamic enclosure, they managed to achieve a 144 km/h maximum velocity. But if we ride a bicycle behind a dragster, I would never do because I would be scared, but in general, Dennis Muller-Korenek managed to achieve 296 km/h, which is impressive. Then we talked about forces, mainly when we are riding a line with where there is no wind. In the first picture on the left, I show also that the cyclist, when it's riding, there will be a velocity of the ground velocity, which is the velocity of the cyclist. But there can be also a wind velocity, which, summing up the velocity of the cyclist and the wind, the cyclist will see a relative velocity called Vr. Now the question is, when we talk about drag or other forces, should we consider the forces aligned with the wind, or with the relative velocity, or with the velocity of the cyclist? In general, in cycling, we use a body axis. Therefore, the forces aligned with the cyclist. Therefore, later when I will talk about drag, I always will refer to the force component aligned with the riding direction. But we can also have a look to pressure, to velocity, to vorticity. And how we do this? We can do this through wind tunnel test, CFD simulation, or field test. Now, I will show in brief the first 2 methods. In general, in a wind tunnel is a tunnel or a pipe, as you can imagine. There will be air moving inside, and the cyclist will be placed on usually on a force balance, and this force balance will provide you the forces and the moments acting on the cyclist. But we can also put pressure taps on the cyclist body, which will provide the pressure on the cyclist, or using optical methods or other methods to obtain information about the velocity. While in the CFD simulation, the usual workflow, the first step is to create a geometry. We can do this through CAD design or acquiring the geometry with a 3D scanner. Then we build the domain and the surface grid. We discretize the surface of the body of interest, in this case, the wheel. Then we create the volume grid. Then we put all the settings, run the simulation, and post-process the data. What I've done in my research was mainly performing CFD simulation based on best practice guidelines, own sensitivity analysis, and research within the group. These CFD simulations were validated with literature available wind tunnel test, and when possible, own wind tunnel test. Then, now I'm going to show the different parts of my research project is constituted. The first part, I'm showing the evolution of cycling aerodynamics. We believe, many people believe that cycling aerodynamics is a very modern topic, but actually it isn't. Even at the beginning of the cycling era, in late 19th century, beginning of 20th century, there was somehow a sort of empirical knowledge of cycling aerodynamics. We found cyclists riding inside the aerodynamic enclosure. This is the first pictures. But also there was the development of a dropped handlebar, which we find still nowadays. But cyclists were also riding behind the motorcycle because they found that while drafting, they could achieve a higher speed. However, due to some ban and of the UCI and the World War II, probably, the aerodynamics kind of disappeared from cycling. There was no aerodynamic innovation, was never taken into account in this age, in these years. While in the late 70s and beginning of the 80s, there is a rebirth. We found the first skiing suite. Then also bicycles started to be built with aerodynamic tubing, and also new handlebar, and both in shape and position. But they didn't make a real outbreak, which happened with the world hour record of Moser, achieved with a bicycle with 2 disc wheels. However, this bicycle didn't have aerodynamic tubing, for example. Therefore, there was still some possibility to improve. And after that, the record, there was aerodynamics start to be always considered in the design of new bicycles. Now, the literature review cover all the aspects. However, here for brevity, I will focus only on the wheel. And as we can see, already more than 100 years ago, there were designed and patented wheels that are the same we consider today aerodynamics, a 4-spoke wheel and a disc wheel. But there was no systematic use of these wheels. And couldn't find a real motivation, but probably is due to the fact that these wheels have a high instability when there are strong winds. Indeed, in these pictures, there are 2 bicycles with aerodynamic enclosures and 1 bicycle with disc wheels, and that bicycle crashed on the last curve due to a wind gust. Then, for 100 years, wheels were not innovated, at least in terms of aerodynamics. But in 1984, we found these disc wheels, and soon after, they were developed 3-spoke wheels and also aerodynamic spoked wheels. For example, wheels with the fewer spoke, aerospoke shape, deeper rim, and narrow tires, and other aspects. And a few of them I will show now. When we talk about the rim depth, is the lowercase d on the upper right corner. In this study from Godot, they tested several spoked wheels with different rim depth. They are going from with the numbers, higher is the number, deeper is the rim. And there was an aerodynamic gain, aerodynamic advantage to have a deeper rim wheel, especially when there is a crosswind. However, this is not comes for free, because what happens is that you have also a stronger side force. And as we see also, the disc wheel has the highest side force, as before we say that has problems with stability problem. Then, if we consider now instead the rim to tire width, these 2 numbers in red, the T is the rim width and W is the rim width. It was found that this ratio should be equal to 1 or smaller than 1 to have the best aerodynamic performance. These internal tests were performed by Crane and Morton in 2018. However, actually it was not new, because there was a patent in 1991 where it was stated the same. It was introduced the 110% rule, and is 110% because in the patent they talk about rim width over the tire width, is the contrary. But in general, the conclusion was the same. However, I want to recap also the limitation of these studies, that they mainly focus on comparing different wheels or different wheels and tires. There are discrepancies between different studies, even 37% of drag difference, and there is a lack of uniform testing and simulation methodologies. And the outcome of all the wheel and the other aspects of cycling aerodynamics are summarized in a paper. Then, the second part, in the second part, I will talk about establish a framework to perform a safety simulation of spoked wheels. Mainly, I will investigate the impact of computational parameters and the wheel-ground contact modeling. There are several parameters. I will talk only about a few of them. Starting with the surface grid. Taking the smallest element is the spoke, as we talked before about marginal gains. Does it make a difference how we model, we discretize the spoke? Actually, yes. Both in terms of computational cost, because if we reduce the size of the grid size on the spoke, the surface grid and the volume grid will increase significantly, and this causes an increase of computational cost, but also in terms of the computed drag. And the results was that the width of these cells should be smaller than 0.167 millimeter. Just to have a matter of reference, a wheel usually has a diameter of 700 millimeter, and we can understand how can scale up the simulation cost. And also that, indeed, we need the small spoke edge size, but not too small, because otherwise the computational cost increases too much. Then the second aspect, I'm talking about the volume grid. and mainly the height of the first cell, which usually describe the number y plus. The general guidelines for the turbulence modeling I'm using for this type of flow suggest y plus smaller than 5 or best equal 1. Actually, from the simulation I performed, the maximum y plus that I recommend is the maximum 3.5 and not 5, and that is always 1. And the number of prism layers, which are these wedge cells over here, the minimum is 12, but usually even more, it's better. Then I investigated the rotational modeling of the wheel. In this type of simulation, there are 3 approaches possible. The rotating wall, we apply a velocity on the surface of the wheel, and then we can apply multiple reference frames. In the first case, which means that we use 2 different reference frames, and in one of them there are added acceleration terms to reproduce the effect of the rotation. In the first one, in the MRF, this moving reference frame volume, that is the one in gold color, encloses entirely the wheel. In the third case, the moving reference frame approach is applied only around the spokes, while in the external part of the wheel, which is a body revolution, a rotating wall approach is used. Now there are 2 questions we can have. Is the size of this moving reference frame volume influencing the results, and which of the 3 is best? Actually, the size of this moving reference frame volume has an influence, and quite high. And I was very surprised that this was never reported, at least to the best of my knowledge, in other computational studies about wheel aerodynamics. And this might also explain some of the difference in the results that in other studies they obtained. Then the suggestion here is always to have a small moving reference frame volume. In both cases, if you use an MRF or a hybrid method, MRF-RW. If we compare the performance of these 3 rotational modeling against with the wind tunnel test, we found that the best model is the moving reference frame with the rotating wall, is the hybrid method, and they give an agreement of around 2%. If we remember before that the errors between CFD simulation and wind tunnel test was even 30–40%, this is quite good result. And the outcome of this impact of computational parameters is summarized in a paper we published in 2019. Then, the other aspect I investigated is the wheel-ground contact modeling. There are different aspects, and also including the zero-yaw angle case and with crosswind, what I will just show the case with zero-yaw angle. Why we need to model the wheel-ground contact modeling? The issue is that if we don't do it, there will be a very sharp angle between the wheel and the ground, and this causes grid issues. The cells will be distorted, and this is not optimal if we want to build a high-quality grid, and the results will be influenced. Then there are 2 possible approaches, is to displace the wheel from the ground or replace the contact with a step, as we see in the most right pictures. In car aerodynamics, this wheel-ground contact modeling has a large influence, but it was not known, in cycling it was never studied, and also we don't know which one is best for our cases and how much should be the distance or how much should be the step height. Therefore, I performed the simulation for different clearance between the wheel and the ground, and also apply for different step heights, but also applying 2 different boundary conditions on the step, a rotating wall and a translating wall. The sensitivity analysis I performed showed that the step height should be as smaller as possible, but a too small step height will also cause some problems in meshing. And also the clearance should be smaller, in this case of 20 millimeter. The difference between the case with the step, with both boundary condition, is almost negligible, is the first 2 columns, while when we have the wheel displaced from the ground, there will be a small difference, about 1–2%. While removing the ground will even increase the drag and the rotational moment. In this slide, instead, I show the pressure coefficient along the tire center line. with the 0 degree is the most forward point, and then moving anti-clockwise. We see that for both cases at the beginning, the most forward point, the pressure coefficient is similar, but moving down at around theta 90 degree, there is a difference when we apply the different approaches, especially the case with the step, the pressure coefficient rise above 1. This might sound strange, but actually it isn't, and because it was already reported also in car aerodynamics, wheel car aerodynamics studies. Then we observe that the pressure coefficient go down when we move in the rear bottom part of the wheel between 90 and 180 degrees. And there are some small dips and peaks, and these are caused by the interaction of the wheel with the low pressure flow, which is detaching from the ground, from the hub and the gears, as we see in the right pictures. And the results of the study, and also the one with the crosswind, are summarized in 2 journal papers that has been published. Then we go to the last part of the presentation and talking about the non-isolated wheel. In this case, we performed the own wind tunnel test at the TU Eindhoven, and we found that my simulation had a very good agreement, 4.8%, which usually when we consider the entire cyclist in the bicycle, it's a very good agreement. And the front wheel had an impact when, in this case, the wheels were kept static, of around 4% of the total aerodynamic drag of the system. Now, in this part of the work, I compared the aerodynamics of isolated and non-isolated wheel. Isolated are the first row, non-isolated are the second row. And when the wheel was static and rotating. Static are the pictures on the left, rotating are the pictures on the right. The first group of pictures is the pressure coefficient, the second group of pictures showing the velocity. Focus on the first group, we see that in front of the wheel, in both cases, static and rotating, there is high pressure, but moving downwards, there is not anymore high pressure in the static case, while we see dark red in the rotating case. Moving to the non-isolated cases, down, there are not many differences compared to the isolated case. The only difference is what I highlighted in white, is that near the forks and the hub, there is a large pressure coefficient. If we go to the velocity, it's also clear what is happening inside the wheel. In the static case, there is a high velocity inside the wheel, while in the rotating case, the velocity is much smaller. And showing the same graph as before, the pressure coefficient along the external tire center line, we see that all 4 cases have a very similar pressure coefficient until the first 45 degrees, the front part of the wheel. While moving downwards and near the ground, we observe 2 different behaviors. One, we see 2 curves, is the blue and the red, are the case for rotating wheel, while the other 2 are not rotating. Where near the ground, the impact of rotation is significant. We have this peak, as we observed before, is not exceeding 1, because in this case I used the clearance between the wheel and the ground. And then after this peak, there is a dip and several oscillations in the rear bottom part between 90 and 180 degrees. And this again was caused by the interaction of the wheel with the low pressure flow that is generated from the hub. Moving in the top rear section of the wheel between 180 and 270, the situation changed, and we observed that there are still 2 groups of behaviors, but now what makes the difference is the fact that the wheel is isolated or non-isolated. As we see, the purple and red line are the non-isolated case, and this dip around 245 degrees and the peak at 255 degrees is caused by the interaction of the wheel with the down tube and the forks. And while going back in the front part of the wheel between 315 and 360 degrees, there is again all the cases show a similar behavior. Then we can go to the conclusion and novel aspect of this research. We found that even how we discretize the spoke size has an impact, and that we should have a small cell size for the spokes. The prism layers, we should have a Y plus smaller equal than 3.5 at least 12 layers. When we apply a moving reference frame volume approach in the hybrid case or not on the full case, we should have the size should be kept as minimal as possible. For the distance between the wheel and the ground should be at maximum 20 millimeter when there is no wind, or 10 millimeter with the wind. And the step height should be maximum 10 millimeter. And then we also made some flow visualization to show how the flow is behaving around the wheel. Then the last part of the conclusion, these are also some other results which I didn't talk before. We found that there is the main difference in the pressure contour are caused by when the wheel are static or rotating. The rotational moment also has a large influence on the performance of the wheel, and often this quantity is neglected, while it is important to be able to quantify the performance of the wheel. And it has also an impact on the total cyclist bicycle case. Then we found the low pressure flow region that we identified before for the wheel case are also found for the non-isolated case, but only if the wheel is rotating. And yes. And the novel aspect of the thesis is that I provide a comprehensive review of the evolution trends in cycling aerodynamics. There was a first detailed quantification of the impact of computational parameters and also of the impact of wheel-ground contact modeling. I provided CFD guidelines to perform simulation of spoked wheels and also flow visualization around the spoked wheel. And then we also get more in depth about the effect of the rotation on the wheel. And also I compared made comparison between isolated and non-isolated spoked wheels, which was also new. Thanks.
Can I speak from this side?
Yes, no problem.
It's a multi-directional one. Okay. So this concludes the first part of this defense. I have now the pleasure of introducing the examination committee to you, who will start with the questioning. And by the way, anybody in the public also can ask questions. So we'll be able to see them. Oh,
well, only
okay.
here. We can hear.
Oh, all right. So first member of the jury who will ask questions will be Professor Owen Clifford from the National University of Ireland, Galway, Ireland. And perhaps I should ask, Owen, are you with us?
Hello.
Okay, I will continue presenting the jury. I just want to make sure that you know you're in touch with us. Okay, second will be Professor Frédéric Grappa from the Université de Bourgogne, Franche-Comté in France, of course. Frédéric, you're there.
Yes, I hear.
Okay. Then third is present here will be Professor Bat Nicolai from the Faculty of Bioscience Engineering. He will be followed by Professor Johan Meijers from the Department of Mechanical Engineering here. He then will be followed by Dr. Twan van Hoof, who is also Secretary of the jury, for which my thanks, from the Department of Civil Engineering. And then we come to the supervisors. One, Professor Hamid Montazerin, will ask us questions from the University of Technology Eindhoven. Hamid, you're with us?
Yes.
Okay. Your turn will come towards the end, as you can understand. And then finally, Professor Bert Blokken will conclude the questioning from the jury's part. My name is Omer van der Biest. I'm representing faculty and university in the jury. So I'll give the floor first to Professor Owen Clifford, please.
Hello, Fabio, and hello, everyone. And sorry, I couldn't be there today from Ireland, but obviously traveling is difficult. I have to open by saying that I just learned 5 minutes ago that an Irishman, Sam Bennett, won today's Tour de France, the stage of today's Tour de France in a sprint. So I think that's quite fitting considering this thesis. So firstly, congratulations again on your work, and thank you very much for the presentation. Obviously, the thesis is very interesting for me. And I suppose one of the areas I was just wanted to ask, I'm conscious of time, and I have 3 questions I would like to ask. And the first one you mentioned in your presentation regarding the lack of uniform testing in previous research. And it's something that in your literature reviews, which were extremely comprehensive, you referred to quite a lot. I'm wondering, what were the implications? What do you believe the implications are in general, for the results that have been developed to date? In other words, how can we say trustworthy are those results? And secondly, where do you think your main achievements are in helping to perhaps give more certain guidelines in the area of wheel aerodynamics?
Okay. Thanks for the question. If the results are trustworthy, usually we believe that when the research is done and published, we should believe these results. Of course, there are some discrepancies, and what I've highlighted, for example, what I've seen, I've investigated, for example, the 2 cases I showed here, the wind tunnel of Greenwell and the wind tunnel test of Tue and Sawyers. I found that there are some discrepancies in the way the tests were done. For example, the open test section, closed test section, and this has also an influence. But another part that had an influence is that Greenwell tested the rear wheel, which had also the gears, and this also has an influence on the drag, and was not even clearly mentioned. And also the tire they used. As we saw that the results from Crane and Morton, there is a high influence of the tire on the tire size compared to the rim size. And usually the tire size is not reported in many studies, but also the same tire will fit differently in a wheel. What I've seen that is important to have a trustworthy methodology, but also report in a clear way the components that were tested. What I tried to do in my simulation is always to give the shape of the rim, the shape of the tire I used, so that the results can be reproduced. And this was also a problem when I was studying the previous literature. Usually the shape of the wheel is not clearly identified, provided. And we see that even the smallest element, the spoke element, can have an influence, and this is causing a lot of this discrepancy. I hope this answered partially the question.
Yeah, thank you very much. It does, yeah. I think you make also a good point around in publications clearly specifying what are the conditions of the test, but also exactly what you are testing. So whether the conditions of the tire, whether gears have been included, etc. So my second question is, I suppose, relates to the chapter where you are looking at the isolated versus non-isolated wheels. And again, I have 2 parts to this question. One is, I suppose, to do with the overall design of a bicycle. And as you may know, many of the wheel manufacturers are separate and different companies to frame manufacturers. And so they often, and probably in general, work in isolation to each other. So the first part of the question is, really, is there any benefit if you're looking at the difference between winning and losing is 1 or 2%? Can wheel and frame manufacturers continue to work in isolation? Because obviously the wheel has a big impact on the aerodynamics of the frame and vice versa. And the second part is, given the work that you have done, why in the future, or do you think anyone in the future should continue to model isolated wheels, isolated stationary wheels on their own? Or with the guidelines you have given, do you think that that type of modeling is obsolete?
Yes. Thanks for the question. Depending a lot of for example, if we talk about safety simulation, it depends a lot also about the computational power, for example, a manufacturer has. I'm talking now, answering the last part of the question. And I would always try to simulate the wheel as most complete as possible, but when we have also many wheels to test, to simulate, sometimes can still be have a benefit to simulate the wheels isolated from the rest of the bicycle and the cyclist. If this is the way to go, it's a challenging question because it's difficult for a manufacturer to produce every type of components. And as we see, there are really a large variety of wheel manufacturers. Only for the Tour de France, there were only 14. And what the companies should do, at least the cycling team should do, in my opinion, is that once they have a frame, they should test as many wheels as possible to try to identify the ones performing best for their case. But here, the complexity of cycling aerodynamics doesn't help, because then we can have also a different cyclist. Different cyclists also might be larger in size or smaller. Then the bicycle will be also smaller or bigger. And I always believe that at least for elite cyclists, for the top, we should always test everything together. Maybe first we can split the problem, like isolated wheel, the bicycle itself, but then the final optimization has to be done all together. For the other cyclists, which maybe cannot afford to go in the wind tunnel or the cycle, we should have some more also guidelines about, I think they should rely on the aerodynamics of isolated component and without testing, because they cannot afford, for example, the test themselves.
Okay, thank you. That's a good answer, and I agree. I think there is some debate and some perhaps criticism as to whether cyclists should rely on these type of, we call them isolated tests, but I agree with your answer that of course not everyone can have the facilities available to the top professional cyclists, and so the general guidelines that you can get from this type of testing are still very valid. And my last question, I suppose, actually has to do with maybe more just a technical area. I was interested in the chapter looking at the ground and wheel and ground contact, as to if you could explain to me maybe at 10 degrees yaw, what was happening that causes your advice, your guidelines to change in terms of either the distance between the wheel and the ground or the actual height of the step. So at 0 up to 10, you have one set of guidelines, and then I believe at 10 and above, you have a slightly different set of guidelines. And could you explain what's happening there?
Yes, I can. Let's think for simplicity the case with the step. I think I also presented one slide, but now it's complex. Can we put the slide, Natasha, as well? No. Sorry, because with the slide it's better. Okay, this slide. Okay, now we see. For example, as we see the bicycle as a footprint, in this case was with the step, the last pictures on the bottom, which is change in size when we change the step height. But if we think to case with the crosswind, let's rotate the wheel. The front part of this step that is facing the incoming wheel is much bigger, because I don't know, if we're just thinking of rotating, then it's not so slender anymore, but it will be more bluff. I hope this answer. And this is causing also why the size, since the size is increasing, then it will cause the differences in the guidance.
And this is above 10 degrees yaw. This the clearance that you require doesn't need to change further, you believe?
It might change. I didn't simulate.
Okay.
I didn't simulate it. They might change, but we need also to think about that the probability to encounter wind at 20 degrees is much lower. That is why I focused on until 10 degrees, because it's most common.
Okay, that's all the questions I have, and thank you very much for your answers.
You're welcome.
Thank you, Owen. Professor Grapp, please.
Fabio, thank you very much for your great presentation and the very interesting presentation. Your presentation very complementary according to your book PhD, and so it's very, very nice presentation. So my question will be rather on the general use of the result of your thesis, more on the practical field, and because our problem, the current problem on the teams, is to try to make the better choice according to for the wheels according to the field, and our problem is what is the better choice for climb flat field, and also when you allow a lot of acceleration during the certain phase of cycling. For example, where rider are in during in effort in 7% slope, for example, the speed of the bike is not a linear speed like that with different phases of acceleration, and you have a lot of kinetics energy. And if you take, for example, a wheels within not important height, but with a poor stiffness, it's difficult. So height, inertial of the wheels, aerodynamics, and stiffness is the four parameters that's very important for us to make the better choice. And my question is, according to your opinion, what is your advice for the choice for the better wheels for time trial, for climb on the hilly terrain, hilly field, and with you have a lot of acceleration phase?
Thanks for the question. This is really race dependent. It depends from the, as we say, the type of races like time trial, climbing, but also on the, for example, on the weather condition, if we have a lot of wind or not so much wind. In general, when we are on a flat stage, aerodynamic is the most important, or a flat stage or almost flat, always go for the most aerodynamic wheel. Like this wheel, three-spoke or spoked wheel with deep rim. This is what is usually done. When there are acceleration, of course, there is the influence of the inertia of the wheel, and this is I have not really data about that, but it should be really wheel dependent, and we should check the tables of the wheels to understand. But for climbing, it depends a lot how much time the cyclist has to climb, and I think the best answer would be to plug in to put in a mathematical model the condition of the race and the different type of wheels, the characteristics, and from that it should be able to understand which of the wheel is best. Of course, the best is always that if it has all the characteristics, that is light, that is aerodynamics, but in general, also sometimes I see spoked wheel with a medium depth, which are fine also due to the stability when there is crosswind, but they really depend a lot on the velocity where you go. As I shown before, also when climbing, then the most important quantity is the potential power loss. But aerodynamics still play a role. Then if we manage to get a light wheel, but still quite aerodynamics is best. But I think there is not one answer to this question. I can provide you the holy grail of the.
Yeah, it's the balance is very difficult for us and for the riders, and because when you are in a climb after your descent, on the climb descent, the balance between these two conditions is very difficult, and try to have the better balance is not very evident for us and for the riders. And
it's important. Sorry if I interrupt. It's also important how the cyclist feel with that wheel, because at the end we also always have the cyclist. If the cyclist doesn't feel good with that wheel, there is not much you can do. It will go slow, even just because thinking that wheel is not good for him. It's everything is very complex, I think.
Also, my second question is about also important interface between you spoke about that between the shape of the rim and the dimensions of the tires. There is a lot of problematics about that. Some people think it's better to have the ratio between the shape and the width of the tire and the size of the rim according to the front wind and the different yaw angle of the wind. It's not very evident to have to take the good choice. And in your opinion, what is your opinion about these problematics on the in the future? What do you think about that? For the ideal, it exists an ideal shape, an ideal ratio between these two parts, rim and tires.
Yes. Natasha, can you plug the presentation? Just a second. What I can talk is about this study was made by Crane and Morton in 2018, and I didn't specify before, but the quantity, the drag area on the left in the vertical axis is actually an averaged drag area, which takes in account also the influence of the wind. It's averaged between different yaw angles. And according to this study, but there is some variability, especially for the low T/W ratio, which means the ratio between the tire width and the rim width. Usually it's best to have a tire that is slightly narrower than the rim. And the explanation is probably that if you have a tire much larger, then the flow separate and they will not reattach and they will not exploit the aerodynamics of the rim. While even if the tire is slightly smaller, maybe there are some separation, but it might be able the flow to reattach and follow the rim shape. This is the explanation I gave myself. And also the patent before confirmed the same results. I didn't test myself, but in general, I would always go to have a tire width which is the same or slightly smaller than the rim width, and try to have also the space between them as, let's say, there is not much space between them, and the transition between these two components is smoother as possible. This is what I would do.
And what is also your opinion according to the interface between the rim and the tires? Because if you, I don't know if you know the regulation, the rules about that, you are not the right to put the rim on the tire. Sorry,
Sorry, I didn't understand. Can you repeat, please? Sorry, there was no connection.
I lost you. Okay, my question is about the interface between the tire and the rim. The rules of the UCI rules say that it's not the right to put a surface between the two parts. And sometimes you are not a perfect shape between the tire and the rim. And so, what is your opinion about that? You think is the height of this interface is important or is not important?
It might cause some flow separation, some recirculation bubbles over there if there is too much space. The best, at least what I've read also in some papers in the past, that they say that this transition should be as smooth as possible. But I would really suggest to check different tires, because what was reported in Crane and Morton 2018 is that they tested different tires, and even the same tire, which was a nominal width of 23 millimeter, when tested on different rims, had a different shape on it. And then it's really kind of trial and error to find, in my opinion, the tire that fit best the rim you have, the wheel you have. This is...
And do you think with currently with the CFD method, it's possible to assess this interstitial on rim?
It is possible to make the simulations and check the influence of this transition, but the main issue I see, but it's solvable easily, is that we need to make 3D scanning of every wheel and tire, or every rim and tire, because since the tire fit differently on different rims, we need to know exactly the shape. And once we know exactly the shape, then we can perform every simulation. In the CFD simulation, I can recreate myself, as I did, the shape of the tire, but then we are not sure that the tire from that brand really fit in that way on the rim. But to have some guidelines to see how it behaves, of course, is possible. I can create a different tire shape, the different width, and then make the simulation for the same wheel and see how it performs. But then we need to ask ourselves, if this tire I created myself is a real tire? This is what maybe it's can be questioned. But if we will be able to scan, 3D scan the tire and the rim, then it's we can do whatever.
Okay. Just my last question is about the complementarity between the current aerodynamics method of investigation, wind tunnel, CFD, on field. These three methods. I think it's very, very important to use these three different methods to try to have better understanding of different aerodynamics effects. And according to your opinion, what for the future, what is for you the better complementarity between these two techniques, these three methods?
In my opinion, I'm always a big fan of every method applied, because I think every method has its own advantage and disadvantage. Like in CFD is nice when you have to create a new manufacture a new component, because you can create from scratch. I can make my wheel design without really creating it, which can be also a limitation of the wind tunnel. The wind tunnel also is advantages, but for example, field tests I found very useful also for the training of the cyclist. If you have some equipment that measure the drag, maybe even if it's not perfect, but still can give an indication to the cyclist while he's riding, for example, on a track. Therefore, I really think that we need all the three methods and try actually to combine as much as possible. In many cases, I've seen CFD simulation of wheels that were not validated, but you need a validation to understand if your model is correct. For example, here I see a complementarity, but I do believe that we need really to push on all the methods and try to exploit as much as possible, because we are always talking about the differences in races. Sometimes can be big, but sometimes you can win really for 0.3 seconds. And if the cyclist can train himself with some field tests, even if they're not perfectly accurate, but still maybe they can provide an advantage to him or her.
Thank you very much, Fabio. Thank you very much for your responses, and again, congratulations for your great research work. And I wish you a great career. And I hope to continue. I think to work with you in the future. Thank you very much.
Okay, thank you, Professor Graff. Professor Nicolai.
Thank you, Mr. Chairman. Fabio, I also enjoyed your presentation, and also reading your thesis was a little bit thick as I went my way through it. I would like to continue on the last question that was asked, which is about validation. There's not too much validation in your thesis because you focused on CFD modeling. You did use some wind tunnel experiments that were published and so on, and you also highlighted in your conclusions that this is certainly an area where somebody has to pick up the measurements and the validation studies actually, that's also what you said just a minute ago. But now you don't really know at this stage what your accuracy of your CFD models would be. And I'm assuming that they're quite accurate, but still the model contains some approximations, for example, the fact that you use immense approximation, turbulence model. On the other hand, probably the low-hanging fruit has been harvested already, and there have been many changes and so on, and we are maybe not that far away from the ideal wheel. So my first question is, do you think that the accuracy that you have now with your CFD simulations is high enough so that you can still make substantial changes or come up with designs with substantially different drag coefficients, taking into account that you are probably looking at very small changes of the drag coefficient that is still feasible?
Yes. Thanks for the question. There is, of course, we need to have, as I pointed out, and also you pointed out, that we need also more wind tunnel tests to increase the confidence in our CFD simulation. I performed the simulation with all the wind tunnel tests I had in the literature, but for sure this is the first, one of the first areas which I would, if I would continue on this topic, I would go increase the number of wind tunnel tests and not focusing only on the drag, so that we can have more confidence also in our CFD simulations. Now, the advantage of the CFD simulation is that I can compute the drag on every single component. I can know the drag on the spokes, the drag on the hub, the drag on the rim and the tire. This makes an advantage because, for example, if I measure the drag on the entire wheel and I make some in a wind tunnel and I make some changes, I never know which is the changes which caused me this reduction in drag. In this CFD simulation, we have this advantage. I can decouple. Of course, there will be always some coupling effect. So if you have a different spoke, maybe the flow is different also on the rear part of the wheel. But in general, I can understand which, of course, there is many years that are developing new wheels. But as we see, there are still many other wheels, and there are other parameters also to take into account besides the aerodynamics. This means that if a manufacturer comes with a new lighter wheel, maybe they need also a new shape to be able to use that wheel, or for a stiffness wheel. Then there is also in CFD we can, if they do their calculation with also computational methods, we can check directly if this wheel is also performing well from the point of view of aerodynamics.
Okay, I will take the first answer that you gave, where you said that basically, even if there's some inaccuracy, you can at least use these CFD simulations to prioritize, for example, those aspects that you need to optimize by CFD. Can you assume that that this is even true when there's a small error on the calculations? Okay, so one of the aspects is actually the rider itself. And in fact, you already sort of adapt the handlebar and the seat and so on when the rider or when the bike is fitted to the rider. I probably have read it, but I kind of forgot about it. But you scanned one typical rider for the simulations that you did.
Yes.
But you can assume, or you can expect, that the results will depend on the rider, right? So what do you suggest would you, so in the future, to make, draw some conclusions? Would you kind of take an average rider, or would you define, for example, 4 different postures of riders and do simulations for those 4 different postures?
I would answer first, depending which of the 2 wheels we are analyzing, because the rear wheel is, of course, depending a lot on the flow disturbed by the cyclist and the bicycle and the front wheel. Well, actually, the front wheel, at least in the simulation performed, there is a difference between the isolated and non-isolated case, but it seems more depending from the force the down tube. Because in this case, the front wheel was very close to the down tube, which also was shaped to accommodate the front wheel. In general, speaking in general, I think we need to understand which type of cyclist we want to analyze. I mean, a top elite cyclist or a good cyclist. Because as I said before with the Professor Clifford, there is, for an elite cyclist, I would maybe, still improve the aerodynamics of every single component, but then still is a priority to test him or test her completely. Make a 3D simulation or internal test of the entire cyclist with the bicycle and the weights. Because at the end, we want to make him going faster. And for elite cyclists, it can really be a matter of small margins. For professional cyclists, maybe not elite, then might be useful to have some bodies. Maybe we can make a body which is a kind of body that is like the average European size body for a man and woman, a different position, and then check. But at least for the front wheel, I think the influence is more due to the bicycle than the cyclist. For the rear wheel, no. For the rear wheel, there is much more.
Okay, I want to take this a little bit further. Actually, the idea that came up while I was listening to you, the idea for starting a spin, because you can take that concept to personalize the design for a certain rider. So rather than having some prototype riders, for example, professional riders and so on, you have this company, the spin-off company, and we would hire you as a chief technical officer, of course. And the idea is that the person would come in, and then a full body scan would be made. The body scan would be imported in CFD software. The CFD software on the spots does a design optimization, and actually ANSYS, at least the mechanical engineering module, does have such a tool. And then the whole design is then immediately 3D printed, and then 2 hours later, the customer can just leave on his bike, take his bike with him. Is this kind of realistic, or what are the issues that you would expect that to come up?
The issue, well, I see, might be on the biomechanical side, because a cyclist, sometimes even a small adaptation of the position of the cyclist can improve, for example, the aerodynamics, but can disimprove the power production, because it will cycle in a worse way. At the moment, I see very much trial and error between like aerodynamics and biomechanics. But this doesn't mean that it's not possible. Still, if the cyclists come, some optimization maybe can be done, maybe not in 2 hours printing the tip bike, but somehow something can be done. At least, for example, if we think to elite cyclists, several of them, for time trial, they have a 3D printed handlebar, which is made on their position on the bicycle, perfectly fitting themselves. This is, for example, already done, but only on the handlebar. On the frame, I think that also some cyclists have personal frames with the size built on them. That is still not very common, but might be more common. But the issue is always not only watching on the aerodynamic part, but also on the other aspects. Because if a cyclist is more aerodynamic, but then he can produce 20% less power, maybe he will not be able to win the race. At the end, the scope is always making the cyclist going faster, and the aerodynamics play a key role, but not the only role.
Okay, thank you.
Thank you, Professor Nicolai. Professor Meyer?
Yes. So thank you for a very nice presentation, and I guess that you must be a cycling fan, or you must have become a cycling fan at least. And I think it's very nice that you give this overview also of all the different races historically, the time differences, and how close it can be.
Sorry.
So maybe a first question, and relates directly to the title of your presentation. So the title is Modeling of Real Aerodynamics and its Impact on Cycling. So if you take whatever the tool you have now, on what competition do you think would you possibly have the largest impact? Or could you possibly have the largest impact?
Sorry, the competition of what? Of the wheel or the?
No, what competition? Cycling.
Ah, competition, sorry. Understand. Since aerodynamics played a major role in when the stage is flat, for sure, in time trial, individual time trial.
Like specific, like name a race, name a product.
For example, we have seen that in the first slide, the second slide with Le Mans and Fignon, there was that one was an individual time trial, and he gained 58 seconds on that race, and is really, I believe that the causes were the aerodynamic equipment he had Le Mans. But
I guess I don't know what I mean. Correct me, but I guess if you would have to name the single one which you can have the most impact.
Also track races, but
I guess that would be the world hour record, right?
Yes, world hour record is one of the most.
That is the kind of the most consistent conditions.
Yes. Yeah, because the cycle is also not accelerating; it's going almost at the same speed all the time, and is also flat. And
so I thought what I liked very much in your thesis page. It's page 50. Yes, that's kind of there you kind of give the history of the world hour records.
50, yeah.
Yeah. So and you showed 3 bikes, like you have the 84 Moser bike, then you have the 96 Boardman bike, and then there's the company bike 19. I don't know whether it's an invitation. Oh yeah, you have it.
Yes, an additional slide.
Okay. But I presume there's some bikes in between that we don't see here.
Yes.
Anyway, the wheels are, I mean, probably Moser got it wrong because Boardman did differently in terms of the front wheel. And then companies corrected it again and say like, no, you're wrong. So you know, who got it right? And also imagine you would do your CFD, what could you still improve? Could you improve something? What do you think? How many meters?
How many meters is a bit difficult, but in general, what we see, for example, in Moser, it didn't only use 2 disc wheels, but the front wheel was also smaller than the rear wheel, because at that time this was allowed. Moser, for example, had some issues in finding the correct date to the record, because he made the record on an outdoor velodrome. And there was some wind in some days. Then he had to find the correct spot there during the day to be able to ride with less wind, because otherwise the bike will become unstable. Then also the choice of the wheel, depending if the velodrome is outdoor or is indoor. Sometimes it's also depending about the sponsor you have, because sometimes you cannot really choose the wheel, but it's what the sponsor gave you. What we see, what can be done in general, at least what I've seen, the new bicycle that were proposed for the UK team this year, for the Olympic game that didn't occur, they changed the space of the forks in front to let more space for the wheel, and this maybe to exploit the aerodynamics of the wheel and not having the interference of the fork. But this is what I think they did. There is not really a study about it.
So did they get it right, or was it more, you know, they did something? I mean, in terms of the spokes, for instance, right? That's the most visible difference.
In general, the disc wheel seems always to perform, from the study of Kyle in the 90s, the disc wheel was always like the best wheels, but the 3-spoke wheel, or in case 5-spoke wheel, if they were designed correctly, they could have the same drag almost as the disc wheel. It is why it's, if I don't have the test, it's difficult to say if was the correct choice or not in this case.
And how many % would you still be able to actually gain, you know, say if you take the 19 design, is that already a design that is, it's on wind tunnel, is it on CFD?
In the 90s, the wheel, some were done with the wind tunnel. Nowadays, there is we see both wind tunnel and CFD, depending about the manufacturer. Some of them sometimes are also some magazines that take like 50 wheels, go to a wind tunnel and say test it, and it's also useful to see which are the difference between them. There is still some, I think there is still some drag that can be gained, but not only considering the wheel itself, but also the interaction with the fork, and also the interaction with the tire, because often the influence of the tire on the wheel was not considered. Only 2 years ago it started really getting a bit more clear. I think it's the entire scenario that needs to be. I don't have seconds, but as we see, the record before Campenarts was also done performing CFD simulation and wind tunnel. It was Wiggins, and people thought that okay, this was like the top, but now also Campenarts made it, and maybe soon someone else will manage.
So going back to the title of your
yes.
work, so what race would you think you have the least impact on?
Aerodynamics, about climbing mountain stages. In these cases, the aerodynamics will play smaller roles because the main power loss is given by the potential power loss due to the weight. Indeed, some cyclists even change the bicycle during the race, or like according to the type of race.
Right, then you have to descent and aerodynamics.
Yeah, but sometimes the descent is so steep that it's if you have to brake, then there is not.
I was also wondering about a race like the performance. Do you think that aerodynamics plays an important role there, or is it other aspects?
The aspects are always so many, but in general, there, I think in Tour de Flanders, it will be quite flat stages. I think aerodynamics will play a role, and also how the cyclists will ride together and the teams.
Because I guess the race is very often decided on maybe not on 1 hour, but on 10 seconds of count, right?
Yeah, if you're arriving at the last part.
The question is, would you optimize your bike for that specific moment?
For the sprint, yeah, it might be useful. Also, there was a study from our research group that showed that the aerodynamic in the sprint was mainly on the position of the cyclist, can have an influence. And there were also other studies showing you need always to optimize power and aerodynamics, but if you can gain something on the wheel, this is everything is an advantage, because the wheel will not influence the position of the cyclist, while maybe the handlebar, yes, but the wheel is kind of a free aerodynamics, free gain that you get.
Maybe a last question, a little bit more technical. You also showed this comparison between MRF and MRF RW. And so, yeah, your conclusion is that MRF RW is better. Can you kind of explain that from a physical point of view, why that is?
This was to a comparison with the wind tunnel test, considering the drag. The reason is that actually the spokes are the elements which are like rotating in the wheel, while all the wheel is rotating, but they are sweeping the air. And these is the elements where is the part of the domain where there is really air moving also inside, while the acceleration that will be introduced if you use a MRF method will be much more than maybe that it is actually occurring in a real bicycle, in a real wheel.
Right, so it's essentially the problem that outside of the wheel you accelerate with rotation.
Yes.
While in practice,
there will be very minimal, something minimal that can be taken into account by the RW itself. At least this is what was shown. But that is why I was also stressing in the thesis that we really need the more wind tunnel test, because if I know the flow field after the wheel, then I will get way more insights to compare my method.
Did you see significant differences in separation behavior between the two methods? Because I guess
not much.
Like it's rotating boundary where you then have separation? It's sort of drag?
Not much, because the main drag was caused also in front of the wheel. What I've seen, if you remember the CP plot, the highest pressure coefficient was in the front of the wheel, and something also in the rear, but after the spokes. There was in the main drag component was the tire. I always report the tire and rim together because actually it's difficult to. It's strange to uncouple them because it's actually an airfoil profile. But if I decouple them, I see that in a pro-rotating wheel, the tire is the main component, and especially the front part of the tire.
Okay. Okay.
Thank you. Dr. Van Hoof, please.
So thank you very much, Fabio, for the
Welcome.
very nice overview you gave in the presentation. I'm not at all an expert in cycling, so I have some maybe for you easy questions, but for me they're like interesting. In your presentation on slide 6, you showed the difference between the wheels used by Roglic and one of his
It's
Yates. You mentioned indeed that the time difference can be due to the wheels that they use, for example. Then I was wondering, why does a certain athlete choose a certain wheel? Because it's not like that the twice-spoke wheel, I think, is $1 million wheel or something. So why do they make a certain choice for certain wheels and based on other things like stability or weight or whatever? Can you comment on that?
Yes, thanks for the question. It depends by many factors, maybe also the comfort of also the cycle. Some wheels are more stiff, some others not, and depends also about the sponsor, because every cycling team has its own wheel manufacturer that is sponsoring them, and maybe they don't produce a 3-spoke wheel, or maybe they produce, but it's not as good as the other spoke wheel. Then there are some practical facts like these ones. In general, spoked wheel with deep rim can perform as the same as a 3-spoke, but these, to tell you which one was more aerodynamic, you should really test them or simulate them. Like this, it's difficult to say a priori. But the wheel of Yates seems to not have many spokes. The rim depth is quite the rim is quite depth. Should be quite aerodynamics, but it's difficult to say like was the best choice or worst choice. But as you see, the time difference at the end was 0.3, and you never know.
Well, I can imagine that it's difficult to provide general recommendations for a wheel that indeed other factors play a role as well. You mentioned the practical things like sponsoring, stability, what the cyclist prefers indeed. So yeah, for future research as well, that could be difficult maybe to say, okay, this one should be used because it's like it, or the manufacturer doesn't provide it. Then
yeah. Well, at least mentioning, because Kyle made studies with the many wheels. What he found that is with the 3-spoke wheel, 5-spoke wheel, there was quite a range of, I think, 20–30% of difference between different manufacturers, but the best one were performing as good as this wheel, while the difference between for spoked wheels, the wheels with many spokes, was like 150%, because it really had many parameters to take into account. That is why I was also more curious to study this type of wheel in my thesis, because you can really change rim, spokes.
On slide 57, the topic you showed some comparison between the wind tunnel experiments and the CFD simulation for the non-isolated wheel.
Yes.
So you showed a table here with the values from the CFD simulation with a certain turbulence model, and then you get the values for the wheels, the bicycle, and cyclist. And for the wind tunnel, you only have the overall drag area. If you're really interested in the wheels only, would you repeat this validation exercise, or would you do a different experiment to compare your CFD simulations with them?
What I would do is to repeat the experiment, for example, for rotating wheels, because in this case, the wheels were static. And of course, more wind tunnel data we have, better it is. Then also repeat the experiment for isolated wheel. In my case, where I was really comparing the two situations, isolated and non-isolated, will be ideal. But at that moment of the test, it was not possible. Now it's possible. Yeah. I have to finish the
you would
thesis.
have time left, and because I can imagine indeed that you would like to know what's the drag area of the wheel to compare with. Related to this, it was mentioned already in previous discussions, you have a different methodology. So there's rapid simulations, the reduced scale experiments, and full scale experiments. And you mentioned that all have their pros and cons. But it could be that the team gives you a job, says you have to optimize wheel aerodynamics, and give you 1 month and so many euros, and you can choose one of the three. Which one would have your preference and why? Because you show all the advantages and disadvantages, like all the assumptions you have to make in modeling, also in wind tunnel, the uncertainty in one of the slides you showed in the beginning already for one go angle. So which method would you choose if you have to choose?
It depends by what they provide me. If they don't provide me the wheels, then wind tunnel is excluded. Then I have for sure CFD simulations. Depending about how much money, because usually wind tunnel it's more expensive. Then if they don't pay much, then again CFD simulations. Otherwise, this is my preference. I always like to combine methods. For example, it would be ideal at least to perform wind tunnel tests on a couple of wheels, then repeat the CFD simulation, get validation data, and then maybe perform the simulation for the rest of the wheels. And someone is not with us anymore. So in general, I like to combine when possible, because also it makes stronger the CFD simulation when we can validate directly with the wind tunnel test.
You cannot combine. You don't live in an ideal world. You don't think so.
I would go CFD simulation because I know how to do that. At least I hope.
I have one last short question. There was a figure on page 29 of your thesis about the power, the maximum sustainable power provided by different scientists. And I was a bit interested to see that the line from NASA for first class athletes was considerably below like all the cyclists. So do you know what they define a first class athlete in the NASA results?
Yeah, the NASA results are from 1964.
Yeah.
Also with different type of bicycles. Actually, these data are made from, it's not my graph, I just reported it. Yeah. But I guess reading that is from 1964, I think it's really depending about training material, also how they measured it. Maybe they didn't have the same tools we have nowadays to measure the power output.
You need any medics in there with 1975, so that was not that long after the first class of athletes of NASA.
But the max was much more.
So I was wondering indeed how they defined it, if you would know it.
No, I don't know. I should take the paper back.
Thank you.
Welcome.
Okay, thank you. Professor Montazeri. 2 minutes. You have the floor, sir.
Yeah, thank you. Hi, Fabio.
Hi.
Hi. First, I would like to thank you for all the efforts and your hard work.
Do you have headphones, perhaps? Because there is some. Cannot hear you very well.
Yeah. Is that okay now, or do you still have the problem?
I don't hear you very much. Just sorry for.
Okay.
Hamid, can you talk?
Is that okay?
Yeah, now I hear you better.
Yeah. Okay. I would like to thank you, Fabio, for all the good work and all the efforts to finalize this thesis and to make it very good. I have a couple of questions, Fabio. My first question is actually about the impact of turbulence intensity. In chapter 4 of the thesis, in the discussion, you mentioned that the impact of turbulence intensity on wheel aerodynamics should be conducted in future. My question is, what would be the impact of turbulence intensity and how it would affect your guidelines?
Thanks for the question. I don't have the correct answer because I don't know. That is why I was proposing to do this simulation in the future. But in general, it might be useful to have this type of simulation also to compare with the real world where there might be more flow with the more turbulence intensity. In general, I don't expect significant differences. For one reason is that we have the rotation of the wheel, also the shape, it's complex, and I guess the flow will be really small part laminar, for example, and then transition to turbulence. I guess it's almost turbulence since the beginning. It is why it might have some influence, but not significant, in my opinion.
Okay. So in some part of the thesis, when you are providing the very useful guidelines for people who are working on this field, you are giving very exact numbers. You are talking about 10 millimeters or this kind of very detailed numbers. To what extent do you think your guidelines are valid? And do you think we can call them generalized guidelines or not?
Thanks for the questions. I think these guidelines are useful as a step forward in the state of the art. What I see before, there was quite, if I can say, a bit of confusion. There were so many settings used. Well, now what I try to do is try to give some numbers also to help future researcher manufacturers. One limitation of the study is that these simulations were performed for one wheel. This means that for a different type of wheels, maybe they are not exact, or there might be a larger influence. But in general, I think that can be applied. It's just maybe on the detail of the numbers, maybe some small difference might occur. But in general, I think there should be at least useful, because you know which is the difference that you expect, for example, if you increase the step height. While maybe you understand, okay, for my wheel, maybe I need a bit smaller than the recommendation. But at least you see what is the way to go. Thanks also to the sensitivity analysis that I performed.
Yeah, I fully agree that they are really very useful. So my third question, and maybe last question, is about you already mentioned about, you talked about challenges involved in this, in research on isolated and non-isolated fields. With your current knowledge, if you go back 4 years in time, how you would do this work, especially in terms of working on isolated and non-isolated fields?
Yeah, sorry, 4 years ago, I mean?
Yeah, imagine it would be possible.
What I would do is the way was a bit straightforward, because the issue was at the beginning that since there were so many settings used in the past, at least I would start for sure about the impact of computational parameters. Maybe I would have spent some more time on providing some also result on comparison of different wheels. This was something I wanted to do, but I didn't have time, because I wanted to compare because now I have a set of guidelines and will be useful to apply. And this was what I was missing, and this was I would have liked to do. For example, changing the spoke shape, because playing on really on the advantage of the CFD simulation. We can change the spoke shape, while for a real wheel maybe it's more difficult. And this is some insight that we can gain compared to the internal. This is something that I really would have liked to do.
And what about working on isolated and non-isolated fields? How you would, distribute your time?
the issue was that I don't think I would do much differently, because even if it's very important to understand also the effect of the presence of the bicycle and the cyclist on the wheel aerodynamics, it's also true that there were many parameters that I didn't know how they should have been modeled, like the impact of wheel ground and the ground, because now it's easy to say, okay, it has a limited impact as soon as you use certain settings, but before I didn't know, and it's I don't know how much I could have changed my time to apply.
Okay, yeah, thank you very much, Fabio.
Thank you. Professor Blokken.
Just a second. Sorry, you're not online there? I think the problem is that. Just a second. Start cam.
One question for you, Fabio, because we had a lot of discussions. Do you know Stefan Kuhn?
Yes. That is not personal.
Not personally. So about 2 weeks ago, he became the new European champion.
Yes.
Do you know which team he's riding in?
The Groupama DJ.
Do you know which bicycle they're riding on?
Yes, Lapierre.
Yeah. Maybe many people don't know that, but it's a bicycle where actually you did a lot of work for the design. So I'm going to ask you a very personally difficult question. How much do you think that the new bicycle contributed to this victory compared to the old one? And the difference between Stefan Kuhn and Rémi Cavagna was 17 seconds.
As we have performed the simulations, we know that there is a difference between the old and the new version, and it provides for sure part of the advantage that the Stefan Kuhn got was also thanks to the aerodynamic of the bicycle. But yeah, there is always, cycling is so complex that there are so many aspects. There is a contribution also from our side, from our simulations, but for sure it's always the cyclist who is riding at the end. And I think he has the largest contribution in Trista, but still some of the advantage he got was also thanks to the bicycle.
Do you have an idea of what would, say for example, a 1% improvement on the bicycle, what would that give in terms of the improvement overall on such a time trial?
I don't remember what the time trial was built. I didn't compute it, but yeah, I don't. Sometimes it can give some several seconds of advantage, but I don't know by heart how much. I don't know. Did you calculate?
No, not yet. That's why I'm asking you actually.
But we can do it afterwards.
Okay, thank you very much.
Away.
Okay, thank you. Professor Blokken. Any questions or remarks from the audience here? Any immediate takers? And time is rather advanced, so I think it's time for the jury to come to a final conclusion.
Yes.
So we will be back shortly.
Ja, oké, er zijn heel veel vragen.
So, okay, I'll, this is the mic that works, right?
Yes,
Okay.
you can
All right.
hear in front.
Well, wherever, as long as people hear me, it's okay. Dames en heren, geachte collega's. Ik geef u kennis van de uitslag van de beraadslaging van de examencommissie aangesteld voor de proef van dokter in de ingenieurswetenschappen. De heer Fabio Malizia heeft aan de faculteit een proefschrift voorgelegd handelend over Modeling of Wheel Aerodynamics and its Impact on Cycling. In het Nederlands modellering van wielaerodynamica en de impact op het wielrennen. Dit tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. Hij heeft het proefschrift in een openbare zitting voor de examencommissie verdedigd. De examencommissie heeft vastgesteld dat zowel aan de wettelijke en decretale bepalingen als aan de voorschriften van het universiteitsreglement ter zake werd voldaan. Na beraadslaging verklaart de examencommissie dat de heer Fabio Malizia voldaan heeft aan alle eisen voor de proef en de graad van dokter in de ingenieurswetenschappen behaalt. In English, especially for you. Mr. Fabio Malizia, the examination board has concluded that you have fulfilled all the requirements laid down in the university regulations for the doctoral examination. Therefore, on behalf of the rector of the KU Leuven, I confer upon you the degree of Doctor of Engineering Science in the field of Civil Engineering. In het Nederlands, bij gevolg en in naam van de rector van de KU Leuven, wordt de heer Fabio Malizia gepromoveerd tot dokter in de ingenieurswetenschappen richting bouwkunde. The official session is closed, but we still have two speeches. One by the promoter, Professor Blokken, and one, of course, the new doctor. He has the last word. Okay, we can sit down, fellow junior members, and take off our hats.
Dear Fabio, dear Dr. Malizia, normally I write 1 page of speech per 100 pages of thesis, so you made me suffer this time. On 18th of April 2014, you wrote an email to me to inquire about the possibility to do a PhD study in the building physics section here. And you wrote this email after having followed the online course on sports and building aerodynamics. And I think I can speak on behalf of my colleagues here that we get this kind of emails about 100 times a year. Your email, however, was different. It was written in a single font size, a single font type, and in a single color, and without spelling mistakes. So I replied to you. We started chatting about a possible topic. You indicated your love for cycling aerodynamics, and the rest is history. Later that year, you applied for a scholarship to, as it was called at that time, the IWT, and so the Institute for Promotion of Science and Technology in Flanders, which now is called FLYO, and partly FW. And you succeeded actually in writing this proposal and defending the proposal with the top score. And this provided you with a 4-year PhD scholarship. And the title of your project at that time was Modeling of Cyclist Aerodynamics and Heat and Moisture Transfer for Optimal Performance and Clothing, a scope that could have taken you 40 years. So it's indeed quite a lot from what you have actually presented today. I hope that you do not mind that I mentioned that the start of the PhD project was a bit difficult. You worked on several topics such as drafting in echelons under crosswind and cylinder aerodynamics, representing cycling aerodynamics, but these parts of the work never really took off. However, after 2 years, you made some radical changes, and actually a step function occurred in your work. You started to focus on the wheel aerodynamics, in which you really found actually a topic that needed investigation and in which you could really exploit your talents. Of course, in doing so, you used the knowledge and the experience you gained in the first 2 years of your thesis. You also decided to write 2 comprehensive literature reviews, which I honestly believe are really 2 jewels in the field. I think this is corroborated by the fact that this first paper has received compliments by both people from academia in cycling science, but also from professionals in the cycling community. Completing the thesis has cost a bit more than 4 years, but I think it is important for the audience to know how much extra work Fabio has done. That is not included in the thesis, otherwise you would have a speech of 10 pages. He has worked on the project of the Ineos Challenge, which has allowed the Kenyan athlete Eliud Kipchoge to run below 2 hours. He has been working with the French bicycle manufacturer Lapierre and the top French cycling team Groupama FDJ, in which he actually helped them to design the new bicycle, both the road bike and the time trial bike, which also costs a lot of time and a lot of energy. And this is indeed the bike that Stefan Kung rode 2 weeks ago when he became European champion in the individual time trial. And indeed, like Fabio indicated, there's an answer to my question. Success in cycling is always the combination of many pieces of the puzzle, but all pieces of the puzzle needed to fit. And Fabio for sure made sure that this piece of the puzzle also fit very well. He has also helped with many other projects, and actually to the extent that we now really have a problem, because it's not easy to replace someone that does so much extra work for the group. It might be difficult sometimes to understand for the outside world, but a PhD thesis is not only fun, it's also sometimes stress, and there's also always a lot of problems to overcome. And that's normal, because if a PhD study would just be enjoyable and relaxing, anyone could do it and it would have no value at all. So I know it was not easy, Fabio, also for you, not in the last year, but you did it, and you performed a great deal of excellent work, both in quantity and quality. And I think this is also indicated by the fact that almost every chapter has been published or will be published as a paper in a peer-reviewed journal. I have no doubt that also your family is very proud of you, and I especially want to address a few words to them here. Alla famiglia di Fabio è stato un grande piacere e privilegio lavorare con Fabio. Vogliamo ringraziarvi per aver cresciuto una persona così grande e un eccellente ricercatore scientifico. Fabio ha fatto un lavoro assolutamente fantastico e anche ingenuo come persona, e sempre amichevole, sempre gentile e pronto ad aiutare gli altri. Avete fatto un lavoro fantastico. Potete e dovete essere molto orgoglioso di lui. Di sicuro noi qui alla Leuven University siamo molto orgogliosi di lui. È un peccato che voi non possiate visitare la nostra università e la nostra città oggi. ne qui serate sempre I benvenuto. Grazie mille. I also want to thank the members of the committee, Professor Fred Grapp, that maybe is also still online with us from the University of Besançon in France. So he is actually the performance director of the cycling team Groupama FDJ, which I think, as you know, is one of the top teams in the world. Now also with the European champion in their ranks. I would like to thank Professor Owen Clifford from the National University of Ireland in Galway. And he's not only a civil engineer, but he has also been a top athlete himself with, I think, a gold and a bronze medal at the Olympics in Rio, 3 times gold at the World Road Championships in 2014 and 2015, and so on. I also want to thank Professor Bart Nicolai and Professor Johan Meijers, respectively from the Department of Biosystems at this university and the Department of Mechanical Engineering of this university. I think we know each other already for about 15 years, and we regularly invite each other to be assessors of PhD students. And I think for each of us, that's always a lot of work, but at least from my side, it's also always a pleasure and a privilege to work with you. So thank you very much for your contributions. I want to thank Dr. Twan van Hoof from our own department for his many contributions to the thesis, but also to be the secretary of this committee, because someone needs to do it. I want to thank Dr. Hamid Montazeri, who was actually previously an FWO postdoc fellow here, and that actually coincided with Fabio's PhD directory. So thank you, Dr. Montazeri, for all your efforts for this thesis. And finally, I would like to thank Professor Emeritus Omer van der Biest for his willingness to chair all the parts of this defense procedure and for his supervision of the whole process. So Fabio, this has been a long speech, almost 3 pages, and I really need to conclude now. And I can still say many things about you here, but I will keep it short. 5 final comments. You've done really great work, not only in your thesis, you've done so many extra things. And I think that level of multitasking is really exceptional. It was a pleasure for us to work with you, as you're such a constructive and supportive person, and not only in the work environment. We, and that is me and all the other members of the team, are very proud that you are one of ours, and you will always be welcome here. We thank you for being part of the team. We wish you all the best for an undoubtedly great and very successful future. Thank you.
Thanks. Okay. Now, I go for my speech. Actually, it's very difficult because usually you start to thank the people you see in front of you, then it makes it very easy. While many people now are online and some here. I will take my acknowledgement. Please try to not forget anyone. I'm sure I will. Of course, I will want to thank first the committee, the online committee and the physical committee here, because it helped me a lot to improve my thesis. I had several corrections, was very nice, very useful. Hamid, that is online for co-supervising, and especially for Bert, because yeah, at the end, as you mentioned, was not easy at the beginning, but at the end we managed to make this project going on, and I think it's a nice project. At least can have also some future, also maybe for some good other students. It's I think it makes a good value. And also for your patience for my English, and was not always easy to read my text, I guess, especially at the beginning when it was always quite messy. Now I hope it's better. And also the presentation, because that email I sent you was exceptional, that I had one font size, one color, but was not always like that. And as you see also from the size of my thesis, I have some problems in the synthesized concepts. I usually write too much. And of course, then I want to thank all the colleagues in Leuven, because it was a very pleasure time to be there to share moments together, because at the end we spent a lot of time at the office, and when you can spend this time with nice people, also enjoy also nice talks, playing some games. It's very nice also when we go out in the evening. But yeah, sorry if I spent some words more for some people, like Christina. Also, we went out a lot in the evenings, and also in the office. We were always willing to correct my stuff, and I want to thank a lot also my office mates, especially the past ones, Wouter and Michiel. I'm the last one, but I'm proud. Finally, I finished my PhD as well. It was really great to have you in my office to make the time very pleasant, because I had a big problem in the office that I was facing 2 white walls, and it was very not motivating, but at least I had you guys that could motivate me a lot, and also to the new office mates. Yumeng, Arash, but also Tuan. I was also office mate with Tuan for a while. And yes, all the professors also in the office, because I think it's also thanks to them that the work environment is a pleasant work environment. I had also colleagues in Eindhoven, because I was some time going in Eindhoven, and especially there was the Italian team of the Italian people, and Raffaele, Benedetto, Alessandro, and Alessio, especially, because they have been really important for me during these years. You helped me a lot. Also Valentina, of course. And you really helped me a lot in these years, and I really want to thank you for this. Then I had many friends also in Leuven, and some of them are here today. And yeah, I call it in acknowledgement as a chat and Tovarishi, because our names in the chat in the WhatsApp. But yeah, here there is Carmen, there is also Francesco. And it was very nice to meet you also here in Leuven. It makes an added value to know you, but also to the others to know. It's difficult to mention everyone. Yeah, I had also, sorry, I'm getting a bit emotional. Yeah, there was also Isabel and Sofia, my Spanish friends, but also I've been part of 2 associations here in Leuven, and I want to thank them, and PhD Society and Backup Night Stories About Failures. And actually, Natasha, I was joining there with both associations, and it was always nice to have something else, because the PhD took a lot of time, but sometimes I was able to do something else. Also a way to distract myself was nice. And then, okay, I was going to church. I had also Italian friends there. Some of them I know that are following now. It's very nice, especially Patrizia and Paolo, because they helped me also a lot these years. Then, okay, there is also Lily, Julia, there is really Annelise, Giuseppe, really a lot. There was also, yeah, I want to thank also Rebecca for the time being. I had also a lot of friends in Italy that hopefully someone are watching me, and hopefully they're understanding my English. But my English is quite Italian. But I had my friends in Forlì, like we had a group called The Crack with them, and there was Maria Pia Rosia. Also, I was in Erasmus in Stockholm. Some of these friends, Felix, I think, is watching as well. But especially I had a very nice group of friends, which, at least in Forlì, was what we call Team Sports, is Adriano and Fabio. And yeah, were among my best friends, and it's really nice that I can count always on you. And even if you are living, because Adriano is living in the opposite part of the world, in Timor-Leste, Fabio in Italy, it's easier. We are friends, and we call it the same way. We are both Fabio. I'm not calling myself now. And also their girlfriend and wives, Armania and Elena, were always nice to meet you and know that I can count on you. Then I have also many Italian friends at my hometown in San Benedetto, where there was the victorious time trial of Roglic. It was actually at the sidewalk of my city. And yeah, there is Marco, Marina, Cristina, Andrea, Antonio, Maria Elena, Simone, Serena, Alessandro, Elena, Mark, Teresa, most of the others, but especially Marco, because yeah, it's also one of my best friends there. I'm very happy to know him. But last but not the least, there is always the family. And yeah, as I wrote in the acknowledgements, they are the safe harbor. Whatever it happen, everything can happen. They are there. Mio babbo, Ivo, Mamma Marcella, Raniera Antonella, Mia, also my cousin. Always, it's nice to have this possibility to always to go there, talk, and having someone to listen to you. It's not something for granted. Per questo vi voglio ringraziare. Siete stati sempre dalla mia parte. Sono molto felice di voi. Grazie mille. And this is, I think, close my acknowledgements. I try to make it short. Open.
There's one more thing you need to do,
Yes.
and one has the paper for this.
Okay.
You get a certificate for
Yes.
your diploma. The real diploma will come later, okay? So you just need to sign for receipt. If anybody has a pen, or otherwise, yeah, you can borrow one.
Where should I sign?
Below here, that you confirm the receipt of the board.
So
I have also something for you.
congratulations.
I have something for the jury members. I hope a small gift. I hope.
We're not going to stop you.
Thank you very much.
Yeah, I think nobody. But you, for that, no, I have something else. Sorry. You see that I like to make things long.
Yes.
I have more. This, because my Italian friends know it. This is a very traditional liquor from my area. These are some bottle of wines for you. But this is the nice one.
Okay,
I didn't close because.
then I can open it.
Yes.
It is a bicycle. Guidelines for CFD, cooking food delicious. Oh. That's right. Okay, thank you very much, Fabio.
Okay, I think we can end.